Okay, so I'm a bit annoyed. I originally just recorded my entire development session, but that was way too much footage for me to sift through in order to actually cut out a video with the relevant bits of coding in it. So I spent a good while just sitting in Vegas trying to comb through the footage before I decided that's not going to happen. Then I tried recording a video where I, in Danish, went over all of the code. And, apparently there's something cursed about the Danish language because my microphone was completely screwed up in that one. So now that I've reset everything, hopefully it should work. I did a mic test and it seemed to function. So now I can hopefully actually demonstrate the game. Well, the progress I've made at the game so far. So the first little thing to notice here is I have all of these squares. They represent walls, and they're the white square rectangles, and they're quite simple. They have box collider and a rigid body 2D, and the rigid body is static. Then we have a player object. That's the blue cube here. We have the main camera attached to the player object. The camera is it has a vector here, noting its relative position, its position relative to the player. It has a horizontal constraint, which is how far to the edge of the screen it can move, no more than 6 units. A camera speed, the speed at which it moves. And yeah, that's about it on the camera's end. Then we have the player. The player is this blue rectangle. Maybe blue was a bit of a bad color considering the background. I can always change that later. Hopefully at some later point I'll exchange it for a proper sprite. The player has a max speed, a current speed, and an acceleration for horizontal movement. So as you can see, the acceleration is 16 and its max speed is 4. So that means that in a quarter second it will reach max speed, which is, rather fast, but it does make the movement a bit less rigid than if we just actually started out at 4 speed. A Y speed, that one is obviously for when gravity comes into play. That becomes relevant. We have the wall filter. This is just a default collision mask. I might modify it later. I'm just using it as an input for a function. We have the jump force, that is how much force we put into the jump. Then we have 3 gravity values. The reason for this is that basically, if we when we're falling, we use the standard gravity here, 12. And on the upwards portion of a jump, we'll use 6 if we're holding down the jump button and 32 if we're not. And what this basically allows us to do is get different jump heights depending on how long we hold the button for. The player also has a box collider 2D, but no rigid body. We look at the code. I need to remove groundhead, we're not using that anymore. Alright, so the camera behavior is rather simple. It has a player reference. It finds the player by saying if it wasn't given the player, it just checks its parents to say if one of them has player behavior, and if it does, it grabs player from that. We can see here that the camera is attached to here as a child. It has a vector that keeps track of the current camera position. It has its horizontal constraint, again how far it can move, and its camera speed, how fast it moves. And then a vector that keeps track of the last directional input from the player. Then in its update, it uses this method to take a horizontal input, and if we press left, subtract 1, if we press right, add 1. So this basically just gives us -1, 0, or 1. 0 if we hold both or no of the left right arrow keys, and then -1 and +1 if we're holding left or right respectively. If the input is positive, say that the last player's direction was 1. Actually, I should be consistent at that. Make these a quarter. There we go. I'm not supposed to be coding right now. I'm supposed to be explaining. If it's positive, we say the last direction the player moved was positive, and then we add the camera speed times delta time to our camera position. Again, remember, camera position is a vector that says the camera's position relative to the player. And we say, but actually, you cannot go higher than horizontal constraint. Similarly, if the direction is left, camera position minus camera speed times delta time, and again, you can't go lower than minus horizontal constraint. And if you don't have a direction, compare the sign of last player deer, the one here, we signed up here, with the sign of the camera position, which, since it's relative to the player, will basically just indicate whether we're to the right or to the left of the player. Then we'll say, all right, get the save the sign of that camera position, and then say camera position dot x minus sign times camera speed. So move towards the player, and then we just check if the sign has changed. That's why we saved it earlier. And if it has, that means we've gone to the other side of the player, and we just want to stop at the player, so the player is centralized. So camera position dot x equals 0. And finally, we set the camera's position to be the player's position plus the camera position. Again, since camera position is the relative position, and the transform position is our world position. Player behavior. We have our variables here. I'll highlight those as they become relevant. At the start, we grab our box collider 2D component. This will throw an exception if we don't have such a component, but if we somehow manage to create a player without that component, that is an exception that I want to get, so that we don't attempt to go on with a player that can't collide. Then we have our horizontal movement. We do the same horizontal input as we did the camera behavior. Then if it's greater than, if the absolute value of our horizontal input is greater than a quarter, and this one I've largely added for the purpose of this greater than a quarter constraint is largely added for the purpose of what if we want to change our input method. Say later on we decide to play with a gamepad, and that one uses an analog stick. In that case, we might want to make a dead zone in the middle of the analog stick, so that a slightly drifting stick doesn't cause misinput, cause constant input, and so that we also don't have to deal with potential pivots. We'll just say x speed plus equals horizontal input times x speed. Again, the horizontal input, which may be positive, may be negative, we don't care. We just take it, multiply it by acceleration and delta time, and add it to our speed. X speed, of course, being the horizontal speed. And then if our absolute speed is higher than our max speed, we just set our speed to be the max speed times the sine of the current speed. So positive is positive, negative if it's negative. You might also notice that instead of doing a proper vector movement, where we are moving with with a two-dimensional vector that has both an x and a y coordinate, I've elected to just go straight for first a purely horizontal movement, and secondly a purely vertical movement. And the reason for that is if we have a situation like this, a diagonal movement would hit the wall, but this method we would actually land on it, which players like it when it, when it looks like they're going to land on something and they actually do land on it. Even if they weren't actually going to land on it, it's nice to cheat a bit in the player's favor, more or less. Alright, if we don't have an input, so this one being a shorter version of this one, it's kind of fitting that we then give a longer version of this one. But it does more or less the same. If we don't have a horizontal input, if we have positive speed, decrease our speed. If we go past 0, set to 0, and vice versa for negative speed. Then we have float x move, which is just recalculate the amount of movement we'll do on this frame. X speed times delta time. Then we want to do a box cast, more or less, a raycast. So we say we take a list of raycasts that we're going to use as the output. And then we say collider.cast, which we give a vector for the direction we want to move in. And then we say give a collider, a contact filter. That's the default filter we defined earlier. Then we say, and for instance, that could include layers. At some point, I might move all of the walls to a special layer. At that point, we could say only do that. Or maybe I'll have some things that I know I don't want to contact with for sure, so I can move those to a specific layer. Anyways, we have our hits. That's the list that we should write to. This one. We have x move, which is the maximum distance that we want to do the cast. Because collider cast, it's basically we do a ray cast, which is an arrow that just fires off and checks if it hits anything. And by default, it can move to infinity and just return nothing. In this case, we are putting a maximum constraint for how far it can move. And when we do a collider cast, we are actually saying, instead of drawing an arrow, which is, an infinitely thin line, actually cast with your entire collider. So we're taking the entire box collider for the player and casting with that. And then true, that is for ignore siblings, which basically just means if we are part of a greater parent object, we might be well aware of other parts of ourselves that we don't really care to check for collisions with. Again, that could also just feed back into the filter if we could include those there somehow. Then once we've made our list of hits, we make a loop through the list. We say if hit.normal x is not equal to 0, so if there is a horizontal component to the normal vector of the hit, because if we look here over in the current running game, the player is actually currently colliding with the ground here, and we obviously don't want this to constrain our horizontal movement. And the way we avoid that is by saying, hey, this the hit here, the vector we get for that, is actually purely vertical. So we just ignore that by saying, hey, that's purely vertical, we don't care for that. And also we want whatever we hit to have a rigid body. We could also, that's one way to do it. We could also check if it, for instance, had a behavior script. We could make a wall script and say, do you have that? But in this case, I decided to just do the simplest thing and say, I've already given the walls a rigid body for future proving in that regard, so I might as well just check for that. Then we say, we have our math, we take the sign of our hit normal vector's horizontal component, which we now know to be non-zero, so that's either going to be 1 or minus 1. And we say if that is not equal to the sign of our current movement, so for instance, if we are moving right, then we are only interested in so for instance, our sign here is positive, we're only interested in the negative here. So that is because the vector for the hit kind of originates from the hit towards us. So we want it to be in the opposite direction. And the reason for this is that if we don't do this check, we'll get stuck on a wall if we run into it, because even when we move to the right here, obviously can't demonstrate it because the bug is fixed, but otherwise it would immediately say, oh, we're touching that wall, and then it would more or less run the entire script for snapping to collision with that wall, and we'd get stuck on the wall. So that was how we solved that. Then we set our speed to 0, and then in order to prevent us from clipping inside of the wall, because that is obviously not desired, we'll grab the wall's right edge and subtract our left edge, or grab the wall's left edge and subtract our right edge, depending on whether we are which side of the wall we're moving into, and then we'll just take our movement and set it to exactly that, so that we'll end up with the distance between our edges being 0, which is, exact contact with no overlap and no gap. And then finally we'll just say, now we have our movement, take our transform position and add that horizontal movement. Then once we've done the horizontal movement, which again, remember I wanted to do that first, now we do the vertical, which starts out with the gravity. It says if we're currently falling, this part, so we just add the normal gravity. Otherwise, if we're ascending, if we are still jumping, use the lighter gravity. Otherwise, use the heavier gravity. Otherwise, we have our jump buffer. When we hit space, we increase the jump buffer, as you can see here. And each frame will then just add delta time to the jump buffer. And you can see we run more or less the same script here, where jump buffer says, hey, we're going to try jumping. So if we are grounded, and we have coyote time, get into that later, we successfully jump. If we are not grounded, we don't jump, and don't have that coyote time, we don't jump. But on later frames, if we're still holding space, and our jump buffer window is low enough, we'll still be allowed to jump, more or less. So what this allows you to do is hit space slightly before you hit the ground and still get a jump out. And this is just for the purpose of feel. Like, a lot of times players might want to jump immediately upon landing, and having a slight buffer helps them time that. Even though they're technically not getting the frame perfect input, they are, they get the satisfaction of having the frame perfect jump, even though they pressed the button a bit too early. And that one has just to do with player feel. Like, if the player thinks they hit it right as they hit the ground, but they actually did hit it a bit too early, they'll probably feel a bit snubbed if they don't actually get the jump. So, by just having the buffer and not telling the player about it, you allow them to get the jump that they feel good about, without them having technically earned it. Then once we've jumped, you see when we start jumping, we set jumping to true. If at any point we have negative speed, reach the peak of the jump that is, or we just let go of space, we stop having the jumping to be true. So that basically just means if you let go of the space bar, you can't repress it to go back to the lighter gravity if you very briefly let go while in midair. Then we also calculate y move the same way we did before. do more or less the exact same cast as we did before. An important distinction is that now we also take our grounded variable set to false, and then if we actually have a hit with the ground, which it's only a hit with the ground if our y speed is negative, obviously, then we just set ground to be true. So, and if our collisions is a landing, then we're grounded. So each frame we technically stop being grounded and then become grounded again, even though we stay underground the entire time. Then while we are grounded, we set our coyote time to 0, and while we're not grounded, we increase it. And finally, we add y to the position. And if we go back to here where coyote time is used, let's see, that's up here. What coyote time does is more or less, sometimes a player might want to jump right as they get to the edge of a platform. And if they hit the button a bit too late, coyote time basically allows us to still give them a jump, even if they technically pressed the button too late. And that again has to do with player perception, because unless you go frame by frame, it will very much look like you actually did do the jump correctly. So therefore, we do the coyote time so that the player doesn't feel like, oh no, I pressed the button in time. I should be allowed to get the jump and not get it. We don't want that to happen. We basically want to lie a bit to the player to tell them, yes, you definitely timed everything correctly, to help them feel like they're playing better than they actually are. Again, like a human can't do perfect frame perfect inputs, so it's okay to tweak things a bit behind the scenes to help them get those inputs that they can't otherwise get. But yeah, that's probably about it for what I've made. I feel like in this first session, I feel like there's one thing I'm unhappy about with this. It's the camera. I feel like the camera is a bit too janky, and I might want to improve on that later, but I'm putting that on the backlog because the camera is serviceable enough for now. So I'll focus on other stuff first.